Good afternoon, everyone. My name is Dr. Krystyna Gielo-Perczak, and I am so happy that we have opportunity to meet on the line. And it was never for me this type of experience, but as well, I am here with my students, senior design students, of whom I'm very, very proud of. And I would like to share this certain material, which I think will be very attractive for you. It relates to the senior design projects, and their success is already presented in the PDF form, and also will be video recorded and available on May 1st online. So more than welcome. If you have any question for me in the meantime, I will be happy to answer. And you see the button chat. So if you can go with any question, I can stop and discuss certain issues which you are very much interested. I would like to share this material. So once again, so this is, I will go, this is the PowerPoint presentation about our department. So just briefly, I would like to bring to your attention what type of capacities we have, and where our students can find the possible employment. It is variety, and I observe also from year to year, it depends from the generation, how they are applying, where do they find the job, very often in very sophisticated companies. And I am very proud that they have capacity even to go to California to ABET company lab, which is very popular, and it's not so easy to get the job. So here is very short introduction. Core faculty is 40 people. Affiliated is additional 35. We have very large lab accessible for our undergraduate students. So biomechanics, biomaterials lab, which I'm providing. There is also bioinstrumentation lab, senior design lab, junior design lab, 3D printing lab, biooptics lab will be open in fall 2020, and tissue engineering lab was already open in 2020. I am very proud of these capacities because it is the space which can be used by undergraduate students. It is not for research for faculty, but it is designated space for our students. Freshman class currently is approximately 90 students. In the past was 130, and undergraduate currently we have 400. Our size of the classes, it depends. I'm providing the lab sessions, and I never go with a larger class than 20 students. So if I have more students in the entire year, there is more lab sessions. So I would like always to interact with my students on the individual, on personal level, that I can see how they follow the material which I'm presenting, how they interact, how they are creative, what type of questions are bringing during these experiments. So all these devices which I'm trying to expose my students are very state of the art, I should say. And they are quite sophisticated in the sense of the software and applications, and also how to operate. So I'm leaving a lot of time that they are familiar, that they can use, record the data by themselves. They see the capacity of the analysis of this software. Mainly, I prefer to use, generally speaking, the professional software. The software which will be used in industrial environment, and they can get the experience during my labs, biomechanics or biomaterials. Even I would like to mention that this started already online, and I had a very two additional lab sessions, very complex, and I was very stressed out, so I recorded the demo lab experiment, so-called the hands-on. But after, I also brought the free version of software that students were possible by themselves to upload on their own computers and to do certain experiments with the software. So if there is obstacle, I'm trying to find another way and just to bring what is the best, and they can meet or face this type of software even later if they will be in industrial environment. I'm saying and making this stress on this particular issue because I was using software Gielo, and this is a group, this is a professional group which absolutely right now it's very active with COVID-19 testing and so on. So it was very nice that they were supportive for our program, and they offer for me 3 weeks free software. So just to let you know on the side, here we have, I'm continuing to talk about our biomedical engineering curriculum. So we have our concentrations in 4 areas: biomaterials, tissue engineering, biomechanics, computational and systems biology, and instrumentation. So every area is supported by strong access to the laboratories and also to the faculty which works in this area. The most important, and probably it will be very interesting for students to know when this program is really changing a little bit when they are choosing these concentrations. So it is during junior and senior years that they should declare in junior year about the concentrations, and they are assigned to the particular certain courses. But during the first freshman and sophomore year, they are the same program for all concentrations. I would like to stop for a moment, and I wonder if you hear me well, and if you have any questions. Once again, I would like to tell you that in audience I have my own students, and they will be happy to support me if I will be not aware about the certain facts which they are facing during the education. So welcome if you have any question. Right, so now let me, I would like to share with you this a very okay. So this is a hard copy, which I'm always preparing in biomedical engineering. It is 61 pages, and these are the projects of our BME students. So this year we have 28 projects. Every project is presented on 2 pages. And you see the variety of the topics. They are tissue engineering, biomechanics, also related the systems in imaging and instrumentation. Very diverse, very attractive for our students. And if I will have your emails, I can also share the content of these projects. I would like to show you how every project is presented. So you see there is a first project which is presented, and there is a short abstract. Also, there is a content what students did, during this year and how they analyze. Some projects are also the industrial projects. We have 2 projects from Johnson & Johnson. And if you will be ready, I can, yes, or there is a most industry-based senior design from our local company at UConn. Yes, so local and like Hologic is our local, and another Johnson & Johnson is located in Massachusetts. And yes, so this is, I'm trying to be very universal and to meet all the expectations, and also it is UConn Health involved in this project. Currently, I have the project also from Dr. Mazuka, who is a leading surgeon at UConn Health, and he also provided the project for us related to RTCA, reverse shoulder replacement. Yes, thank you. Very good question. Is any question? More than welcome. Every question is good. So this is very powerful, I think, experience for our students, that they are, during 1 year, they are exposed to the group of the professors, or one professor, and also the industrial partner. In the meantime, I can also share one video, and I will try. So this is the PDF file. So if you are willing to take a look, I will be more than happy to send to you the copies. Now, I also will go to the, I will stop sharing this, yes, and I will come to the share the video.
RTSA is a shoulder replacement procedure in which the natural anatomy of the ball and socket joint is reversed, implementing a ball-shaped prosthesis on the scapula and carving a socket prosthesis into the humeral head. This procedure is becoming increasingly more popular each year, as it was reported that there were 30,000 operations of this procedure done in the year 2012, and this number has only continued to rise with each year. One downside of this procedure is the high risk of postoperative complications, with up to 68% of patients experiencing some degree of postoperative complication. This can be anything from acromial fractures to hematomas and infections. Our team worked with Dr. Augustus Mazoka's research lab in the Musculoskeleton Institute at UConn Health to aid them in their research, which was aimed at investigating various forces within the body when an RTSA implant is utilized. Our group's goal was to provide some additional insight and support to their efforts through proposing possible testing design improvements, as well as an antibody modeling and analysis of the human shoulder.
Before our design team began assisting the UConn Health research team, they supplied us with data they had collected from previous tests using native shoulders. Here you see a video playing of abduction in a native shoulder using the simulator. Cables are attached to the muscles and a tensile force is applied to them via an actuator, which causes the shoulder to abduct. As shown in this graph that UConn Health created, the amount of force from each muscle that is required to abduct the shoulder is recorded and summarized. Drawings of each muscle are shown to give you an orientation of where each is anatomically. The second portion of our design project focused on using the UConn Health simulator to analyze the stresses in the scapular spine during RTSA shoulder abduction. This video is from one of their previous RTSA tests. During normal movement, muscles contract and pull at their origin and insertion points. This was important to replicate in the test, as the deltoid's origin on the scapular spine, lateral clavicle, and acromion process causes stress in these areas when the muscle contracts. It is believed that the scapular spine fractures caused by RTSA are due to the increased tension it creates in the deltoid and the resulting increase in stress on the scapula. The previous experimental setup only pulled from the deltoid's insertion point on the humerus. Although this was sufficient to gauge abduction angles, it did not replicate the true forces acting on the scapula during abduction.